Hey everybody, Mr. Klein here, coming to you from room 224 in the G Wing, Bloomfield Hills High School. But that's not where I want to talk to you about today. I want to talk to you about a place called 2EG. We're going to be talking about start plus change problems. And, I should mention demographers. Demographers are people who study and describe changes in human populations. And one of their tasks is to predict the future change in the population. And they accomplish this task by looking at rates. What's the rates at which the population is going up or down right now? And so let's imagine that we're studying one particular town named 2EG, Florida, which, by the way, is a real town. And let's suppose that we also know this. As of the 2020 census, there are 3,500 people living in the town of 2EG. We're going to look at 1, 2, 3, 4 different scenarios that we might encounter when studying rates and predicting populations. So first one goes like this. Demographers find that the population of 2EG is changing at a rate that is equal to 30t plus 10. Okay, and we want to write a model describing the population of 2EG as a function of time since the start of 2020. So you're going to need 2 pieces of information. If you want a function, you need a point and you need a rate. Our point is going to be this. At the start of 2020, which would be time 0, there are 3,500 people living in the town of 2EG. And our rate is given by this. Our rate is 30t plus 10. So for instance, at time 0, we're going up at a rate of 10 people per year. And at time 1 year later, we're going up at a rate of 30 times 1 plus 10 is 40. So 40 people per year. So if we wanted an equation in this case, couldn't we just take the antiderivative? Right? The antiderivative of the rate would give you the actual function. Let's see, what would that be? Antiderivative of 30t is 15t to the second plus 10t plus the constant. But we know what the constant is, don't we? That's what the point was for. We know that when we plug 0 in for population, the output has to be 3,500. So this is going to have to be a 3,500 right here. Okay, so there's the function. Given a point, given a rate, we could cook up our population function. And I want to drive home the point to everybody that, like these are actually used to make predictions in the future. So now let's predict what the population is going to look like in the year 2030, which would mean that we need to plug in 10, because it's 10 years after 2020. So in this case, 15 times 10 squared plus 10 times 10 plus 3,500 gives us, there would be 5,100 people is what we predict to be the population of 2EG in that year. All right, so now let's look at a slightly different situation. Scenario number 2. Demographers find that the population of 2EG is actually changing at a rate that is given by this function, which is complicated, and we'll just keep it simple by calling it R of t, where t is greater than or equal to 0 represents years since 2020. And once again, we want to write a model. Now, has the point changed? Now, the point is still that at time 0, there are 3,500 people. What has changed is the rate. The rate is now this nasty-looking R of t function. And we can't use the same approach that we did on the last problem. On the last problem, we took the antiderivative. And we could do that because 30t plus 10 is a simple function. Here we have this function, and this is going to blow your mind. It doesn't have an antiderivative. there is no function that taking its derivative, you would get this. So now we need to use a slightly different approach. The approach is going to go like this. The population of 2-egg Florida at any given time is equal to the population at our start time plus however much it changes by. Isn't this how everything works, right? Everything is where it started plus how much it has changed, right? The amount of money in your bank account is the amount that you started with plus the amount it has changed by since then. Okay. So we need to come up with something for our start and something for our change. And I'm going to argue that our starting value is the 3,500 because at time 0, we're right here. And I'm also going to argue that you can find the change by taking an integral, right? If you take the integral of a rate, it tells you the accumulated change in something. Now I know this says R of t right here. I'm actually going to write R of u du. And don't let the u freak you out. It's just a dummy variable. And here's the reason that we need it. When we put our upper and lower bounds on our integral, we know that we want to start at time 0, right? Because there were 3,500 people at time 0, and we want to go to some unknown time t. So this is our function. The population is equal to 3,500 plus an integral that starts at 0 and goes to time t. And we should be able to calculate the predicted population in 2030 using this. And here's how we would go about doing that. I would encourage you to go to y equals, there's all kinds of crazy stuff in here, and to type in our function, which was 40 sine of 0.1 times 1.5 to the x minus 1, all plus 41. You don't really even have to worry about graphing it in this case. We're just going to go that p of 10 would be equal to plug a 10 in here. So 3,500 plus math finint, the integral from 0 to 10 of the function that's in y1 dx. And it might take a second for the calculator to think about it because this is a big calculation, but there we go. It's predicting there will be 3,847 people living in 2-egg in the year 2030. All right, so we're now introduced to a start plus change equation. Now let's go to yet another scenario. Demographers find that people are moving into egg at a rate that is equal to this, so that hasn't changed. But that folks are also moving out at a rate of 50 people per year. Write a model describing the population. Okay, well, has the point changed? No. The point is still that at time 0, there were 3,500 people. But the rate of change is different. The rate of change is now going to be equal to the rate in, take away the rate out. So we get R of t, take away 50. Right? This is the rate out, 50 per year. This is the rate in, big complicated equation. Well, what does that mean for our population model? It's still going to be a start plus change. And we're still starting at 3,500, but the rate is different. In here we say R of u minus 50. And I'd like to note that there's another way that you could write this. You could say 3,500 plus, and then you could just do the rate in part. And then separately, you could subtract from it that the total, right? This would give you the total number of people that have moved in. The total number of people that have moved out after 2 years would be 50T. So if inside the integral, it's just a 50 because it's a rate. If outside the integral, it's a 50T, which would give you the total loss. Okay, and let me show you that this works. If I go 3,500 plus the integral from 0 to 10 of y1 minus 50 dx, that's going to give me the predicted population in the year 2030, which is, what is that, 3,347 people. Now just note, I used the first formula, but I could also use the second formula and it would work. See, because we could go this. Notice I did not put the 50 inside. Instead, I'm going to subtract 50 times 10 years have gone by, because this is 50 multiplied by 10. And I should get the same answer. And I do. Okay, so there's two different ways that you can write this model. Last scenario goes like this. Suppose that the population of 2egg won't be 3,500 people until the year 2022. But the rate equations still hold true. Okay, so our rate equation is still going to be R of t minus 50. Write a model describing the population of 2egg as a function of time since 2020. Well, if it's time since 2020, then our point is going to change. And it's not the number of people that changed. It's the year when that number of people happened. It's now going to be 2 years after 2020. So it'll look like this. Well, how is that going to change our model? I still want to start at 3,500. And I know that the rate stuff here inside the integral has not changed. So what it's going to change is here. We're still going to some unknown time. But where before, when we were starting at time 0, that meant that the integral started at time 0. Now we're starting at time 2, which means that we're not going to start accumulating here until time 2. And in fact, let's suppose we wanted to know the population in 2020. Then when we put in P of 0, it would look something like this. We'd say 3,500 plus the integral from 2 to, I'm plugging in for t a 0. y1 minus 50 dx. I guess you can't have 0.8 of a person. We'll just say 3,578 people. Note that there's another way that we could get this. We could also, I'm going to copy this formula. Let's suppose that I don't like the fact that these numbers are backwards. I could change this to a 2 and a 0, and then we would have to subtract, which actually kind of makes sense, doesn't it? That if we're in the year 2022 and we subtract the change over the last 2 years, then it will give us what the population used to be. Okay. So that, ladies and gentlemen, is the start plus change equation, and you are all ready to take a crack at this assignment.